Good afternoon, everybody. So my name is Milan Kulkarni. I'm the Michael and Catherine Burke head of the Elmore Family School of Electrical and Computer Engineering. Um, Today, it gives me really a great pleasure to introduce Pramey Upadhyaya. Um, Something I wanted to mention before I get into his bio is that I've been head for basically 2 years now, and Pramey's case was one of the very first cases that I got to present for promotion at the college level, and it was amazing, right, to get to talk about the amazing stuff that Pramey has done, to think about how somebody who's such a brilliant theorist is able to work closely with a bunch of experimental groups to actually demonstrate that that theory is true. And I think we're going to hear about some of the amazing work that he's done in the area of quantum sensing, probabilistic computing, and using magnetic fields to do brilliant things. So let me tell you a little bit about where he's coming from. So Pramey got his bachelor's in electrical engineering from IIT Kharagpur, one of the top IITs in India in 2009, and then he joined UCLA where he got his master's and his PhD. So he received his PhD in 2015 and then stayed at UCLA as a postdoc, but defected for a little while and went to a department of physics and astronomy. But we brought him back to the light side in electrical and computer engineering. He joined us as a visiting professor in 2017, and then we brought him in through our spintronics search in 2018. This was a cluster of people that we hired that work in the area of spintronics. And he's been here ever since, doing amazing work on quantum sensing, on probabilistic computing, on van der Waals forces. And I think we're going to really enjoy hearing about the work that he's done. Is this on? Thanks.
All right. Thank you very much for that kind introduction. And thank you also for Milan throughout these, in a couple of years, but still supporting all the initiatives and various kind of initiatives. And that has played a very central role in me standing here today. So thank you very much for that. And thank you also for this opportunity to discuss our journeys and listen into other colleagues' journeys of how they became associate professors. Today in my journey, I would like to talk about just like what David did, of two major strands. Kathy posed us these sort of very tough questions of what am I passionate about, and how did I become what I become today. And in order to answer that questions, I would like to answer that in the following fashion: is on the left hand side, this picture is an image which I just asked ChatGPT to generate for saying that, okay, tell me how a bunch of electrons interact in a material. So that's what I usually work with, a lot of electrons interacting with materials and trying to exploit their properties to see if we can build technologies of future. So that was my passion. And how did I get to all this, doing all this, is because of another network I would like to talk about today is more on the personal front, how my interactions with various mentors, collaborators, and family pushed me into that direction and trying to understand that. So hopefully I will be able to do all that in next 15 to 20 minutes. Right, so the first interaction that I would like to talk about is to tell you a little bit about me. So where I was born in the central India, in somewhat of a small town, which now sort of prouds itself as the cleanest city in India, where this place where I belong to is called Indore. And I was born to very loving parents and family, my elder sister, my father, and my daughter. Although you may be surprised that this looks nowhere near an ocean, but we are sitting in an ocean. This is because this is just to highlight the fact that this picture was taken at a time as my father was doing a postdoc in the University of Florida here. So I guess all the roots of the science of getting interested to academia originates basically from him. So he was a professor in agriculture university and currently still actively working in that area. My mother was also an academician. She was a high school math teacher. And that's where I sort of, I guess, learned about all the math skills, all my interest in math developed because of her. And my sister, what a sibling is supposed to do, was always trying to catch me doing things which was not right and tell that to my mother. So that, in fact, that's how probably started my journey in the maths. Because I remember up to middle school, I thought that all the subjects are like the ones where you have to memorize everything that teachers tell you, and then you have to just, in exam, just regurgitate sort of all the things that you have learned. And that's the approach I took for math also. So she caught me actually one day reading very loud, trying to understand the problem. So rather than understanding, I was just trying to just memorize. Okay, 2 cows are worth $10. Then how many cows for how many worth are five cows, and so on and so forth. I was trying to just memorize that, and I thought the exam will be exactly same. But in the exam, the cows was changed to buffaloes. And my mother tells me that I went to the teacher and said that the question is wrong. This has to be buffalo rather than cow. And that's she took personally because she was a maths teacher, and she basically just sort of instilled in me this belief that you don't have to learn maths this way. You don't have to memorize maths. And that's how changed my feeling towards math, where it almost she brought to me this kind of cool. It's like a game where you have to just learn very simple rules, and using those rules, you can solve anything, like new problems that are thrown at you. You don't have to memorize things. So that's something that sort of stuck with me quite a bit, and I got interested in maths with that. And then I started to look at any other subjects where I could sort of apply the same sort of phenomenology. And with that, I sort of struck in to this wonderful field of physics, where you, in fact, here you can start imagining new rules also, and trying to apply those new rules. You can create new sort of discoveries, and that was very nicely summarized in these set of lecture notes by Feynman. And I was very much attracted to the way the Feynman used to think about. He almost sold physics as the closest you can get to superpower, right? So it's like with a pen and paper here sitting, you can calculate what's going in stars out there. It was such a cool thing to be part of. So I decided this is the career that I want to select. I want to go in the physics as my main field. Right. And that's why I was kind of excited to be admitted to one of the schools that Milind mentioned. There was this institute called IIT Kharagpur, which has this sort of very interesting track record of producing sort of deep scholars in the field. Some of them are also sitting in this room. For example, Professor Supriya Datta, our star in the ECE, also belongs to that particular school. And I was very excited to be part of the physics department there. Not because of the fact that I got a very high rank, but it was because physics was somewhat unpopular among students there. The engineering, computer sciences, those were more popular. So I ended up getting physics, which I was very excited about. But my parents did not share the same enthusiasm. They said that, okay, no, you have to go to engineering if you want to have a career. And they sort of allowed me to go to pursue physics for 1 year and say, study very hard and change your branch to go to an engineering school. And I ended up doing that. And in hindsight, I think that was a smart decision career-wise. Otherwise, I would not have been standing here today and giving this presentation in an engineering school. So that's how I went to engineering. But there, I was still kind of sad at that time because I wanted to still do physics. Somehow I wanted to do physics. And then this was another human interaction that sort of highlighted the following fact. I learned from one of my senior, Amrik Sarkar, who's also a Purdue alum and was a student in Professor Datta's group, where he sort of opened my eyes by saying that actually you can be physicist in disguise in an engineering department too. And electrical engineering is the place for doing those kind of things, where he sort of highlighted, pushed me to look at the following problem statement at that particular time, which was giving examples of some of the pioneers who were trying to apply this approach. And he introduced me to these two books from Professor Supriya Datta and from Mark Lundstrom, where they were trying to understand how these bunch of electrons in a material, their properties can be exploited to build transistors, which an engineer really cared about a lot. Right? So the problem statement, just to summarize what the main problem statement that got me started in the field was, essentially these chips are the thing that we know right now have transformed the way we play, the way we socialize, the way we do computing. And at the heart of all of this is this little device over here, which is the so-called transistor, which essentially is an electrical switch which goes between 0 and 1. By applying some gate voltage, you can turn it on and off. And these are your zeros and ones. This is how you can encode information and manipulate information and do computation and do all sorts of amazing things. So this was at the heart of all of these devices. But if I zoom in a little bit more, what made this transistor work was the fact that essentially this is a material of the same ChatGPT image, where basically many electrons are interacting with the atoms and with each other and flowing around, and you are just controlling their flow. And that's how you control the resistance of this device. In particular, it was very important. This was the first part where I learned about so-called quantum mechanics, where it was, for this device to work properly, it was important that these electrons don't behave as some particles bouncing around of these atoms, but they tended to behave like waves, which was the quantum leap that had to be taken, and which was not very obvious for people to first make connection to. But once you accept that fact, then the fact that these electrons actually behave like waves, then just like how in our guitar string, we can only, given the boundary conditions, we can only fit certain kind of waves in those strings. Similarly, in any material, we can only fit only certain kind of frequencies, which is governed by these atoms' location. And as a result, the frequencies or the tones that are allowed in any material, they form these sort of bands in energies. And why a material conducts or why it does not conduct, it really depends on how these bands line up. So you can have a material where these bands really overlap and these electrons can flow very easily. That's how we get metals. But there are materials where these bands have gaps, where there's some frequencies which are not allowed missing, and then electrons cannot flow very easily in that, and that's how you get insulators. But at the middle of these two things, this magical material called semiconductors, where the band gap is just at the right level, where by applying external perturbation, you can turn it from a metal to all the way to an insulator. And this was your switch. This is how you create a switch. By applying 8 voltages, you can turn something conducting and make it insulating. And that sort of changed the whole game of computing and changed how we sort of interact in modern society. So that sort of problem statement was very enticing to me, because now you can use physics to do something which has a real engineering impact on people. And the problem statement that got me, the problem statement that around the time that I joined my PhD, that got me into this kind of problem statement was the following, and summarize the following, that the reason why we could go from computers looking like giant rooms to something which sits in our pocket today is the fact that we could essentially maintain the same physics, turning it from metal to insulator by just shrinking this transistor smaller and smaller, and hence putting more and more and more of these transistors together in a chip, and makes that computing power sort of became more and more exponentially growing. So that was the main observation, which was made by a person called Gordon Moore, which famously in the community is known as Moore's law, where on the x-axis is the years, and is the number of transistors, for example, in a chip, is shown in this yellow plot over here, which exponentially grew. At the same time, initially, at least, people were able to also change the frequency at which you were switching these transistors on and off. So the faster you would make them, the faster the computation also became. So they were able to do that also. Up to this point, this was the time that I was just joining doing my bachelor's. And what was an interesting observation was made that you cannot keep on increasing. Basically, people gave up on making the frequency faster and faster. The reason for that is shown in this blue curve over here, because by doing that, the power that you dissipated in making these switches also started growing exponentially. But the technology that was developed at that time, which would remove this power, otherwise your computers would become very hot, and this transistor will not stop working. So the rate at which you can remove the power from it that technology did not grow exponentially as what transistors were going. So we hit that limit, and at that point, people basically gave up making the frequency faster, because that would mean that your power would go much higher. But then at that point, one major question is how long you could continue this trend of still maybe maintaining the power at that level and making the transistor smaller and fit more and more on these transistors, and still getting more functionalities. And that was the approach that people started taking. You started seeing many cores of these transistor chips being put in a computer. So the problem statement then was, people at this point were saying that, okay, this Moore's law is also going to end, then we need to rediscover switches. You need to discover how we need to perform switching operations, and that gave a lot of room for physics. So you to exploit new physics potentially to solve this kind of problem statement. And then in my bachelor's, I got an opportunity to do an internship in US here at Virginia Commonwealth University, and met another person who was also a student of Professor Supriya. He was, I think, the first student of Professor Supriya, where he introduced me to this alternate way of doing computation, which is the so-called field of spintronics, where now we start to think about these electrons are not just waves that are there in the atoms, but they also carry some intrinsic spin degree of freedom, which is, you can think of this an angular momentum like a spinning top. And then this can spin in two ways. You can do clockwise or anti-clockwise spinning, and that also can be used as information, where you can store information as zeros and ones. And then the people are thinking of, can we use this spin degree of freedom to do computation to potentially create these sort of new switches that may be needed in the future. And so this kind of problem statement became very interesting to me. And so next year I did another internship with another professor called Mike Coy, where he introduced me to another very interesting learning. And the next interesting learning for me was, okay, so far I've been talking about mostly these single electrons that are there in these materials, but really there's not just single electrons, there's many of them, billions of them. And you can have interactions among these electrons. And these interactions can actually make all the spins line up. You can make the spins order. And you end up getting something which is very different from just this one single electron spin moving. So this was the concept which famously by a famous physicist coined as the fact that more is different. So suddenly it's not just a collection of these individual spins. You started getting something which actually, the fact that your magnets that these collection of materials start sticking to your fridges is because of the fact that they collectively order and they create this new state called magnetism. And then essentially this fact for the computation purpose was used already in the fact that you can use these magnets to create storage technologies. Okay, so this fact was utilized to create these so-called memory for storage industry. This fact was already being utilized, and what people were thinking at that point was, if there is a way to convert this spin information into an electrical information, we could potentially start integrating it with electronics and create these sort of so-called potentially new switches that are needed. And around that very same time, a Nobel Prize was given to this very phenomena where how you can convert magnetic information into electrical information, essentially known by this effect of so-called magnetoresistance, where depending on how two layers of magnets are aligned, you can get two different resistance states. And you can also at the same time pass current through these, where one layer will start to polarize your spins and impact angular momentum to the other magnetic layer and switch that direction electrically too. So what that means in summary was you can electrically not just read but also control these states, and hence start creating devices by integrating these magnets with electronics. So this sounded again very fascinating to me, and that's brought me to my next step of doing masters and PhD. And I went to join Professor Kang Wang's group at UCLA, who was one of the pioneers at that time to create these sort of magnetic tunnel junctions and to sort of see if spintronics could be used for these sort of alternate computing paradigm. And my hope was to join there as an experimentalist because I wanted to create these devices. But Kang soon noticed that probably that's one of my weakness, in the sense that breaking an expensive equipment may or may not have been the tipping point at that point, where he suggested whether you can do theory also. Let many other group members do the experiments and see if you can explain the results. So that's how my journey of interface of experiment and theory started. And to my advantage, there was a leading theorist in spintronics who was also sitting right next door in the physics department there, who was this Professor Yaroslav Sokolniak. And I got all my physics sort of or theory training in spintronics from him. And I was in this very cool spot where I was just learning all the theory from him and trying to apply it to all the cool experiments that were going on in Professor Kang Wang's group. And that sort of approach led to my basically thesis, which was essentially trying to answer the following question. So the task that I was given as a problem statement was, so as I just mentioned, now you could integrate electronics with magnets, but then the nice thing about this is the magnets don't require any energy to keep the information there. This was the problem in the transistors that was happening. You get leakage and you were dissipating energies, but magnets don't require energy to keep the information there. But when you try to actively control that state, that active manipulation required a lot of energy. Yeah. And at that point, people were looking at more efficient ways of how you can control these magnets and potentially, again, start integrating these magnetic systems with electronics. And for that purpose, the thing that I learned from these two folks here was, so I told you about these electrons are like waves and they have spin, but it also turns out, if Einstein is right, then these waves and spin are not independent of each other. They are coupled, which was called the so-called spin-orbit interaction. Although this is there in every material and it was known, but at that time, what people realized is even for materials where this spin-orbit interaction is not very strong, you can engineer heterostructures and create make materials where this information is not strong, but make them have a very big spin-orbit interaction via proximity effects. And so that was the key discovery that we worked towards, and to the community introduced this idea of using spin-orbit effects, where you can also use orbitals or position degree of freedom to control spin. And that opened up new ways of efficiently controlling these magnet systems, which became the paradigm of so-called spin orbitronics. And this was probably the contributions that I did towards this work was the main reason why I was hired here at Purdue, because at that time Purdue was also getting interested in using the spin orbit effects to sort of strengthen their spintronics efforts. But before I go into this last chapter, I would also like to highlight that right at that time I met my lovely wife, who was also showing us here to show her support, Shivangi, who almost all of her life also lived at sort of the tip of this marker over here. And just because of supporting my career so that I can still keep learning about these electronic systems, she took the leap of covering all the way and coming and joining me to UCLA. She had a very set life. She gave up all that and just joined me for all this. So that's why I'm very, very thankful for her. And when she came here, the next problem statement that I sort of looked at, I joined, as Milind mentioned, the physics department for a little while as a postdoc. And there what I learned about is one more interesting facts of these electrons, is the fact that I told you these electrons are like spins, like top spinning around. That's a bit of a lie, because even this spin degree of freedom is also quantum mechanical. What it means is, just like the position is baby, the spin is also baby. It's not like you have just one orientation of spin. If you don't look at it, it is very some spooky angular momentum, but if you look at it, it will fall into either spinning this way or spinning opposite way. So this behavior is again very at the heart of it, and it's called a quantum mechanical object. It is a quantum version of a bit. It is not just simple bit. It's a qubit, so-called qubit, which such spookiness or such fact that it could be spinning this way and this way at the same time could also be utilized as a resource for doing a lot of quantum computation and sensing. And the one main problem statement here, we exploited this fact was for building so-called quantum sensors of magnetic materials. The reason for this type of thing, the way it works is these sort of delicate quantum coherences that I talk about, that is spinning this way and spinning that way. To maintain this, you have to take extreme good care. It should be protected from environment. That's why we don't see these effects in our day-to-day life, these sort of quantum mechanical effects. But there was this community that was growing, which sort of used this Achilles heel of quantum systems to their advantage. They say, oh, this is so sensitive to environment. Why can't we use this as sensors of the environment? And that's how this birth of quantum sensors was there, where you could use the magnetic interactions with materials to learn new things that you were not able to probe earlier. And the systems where these are housed are in the so-called diamond nitrogen vacancies in diamond. So these are not the kind of diamonds probably which my wife would like, but these are the ones which have defects in them, and that defects holds these spins, which can be used to do this sort of sensing. So with all that, I was then for my next career move, I was again very lucky to be hired here at Purdue, because Purdue at that same time again became interested in spintronics. And this was the case of me being in the right place at the right time, where in one of the conferences I met Professor Supradatta. Finally met him once for my life, and then he suggested, why don't you apply, because we are looking for people in this spintronics team. And when I was given the offer, I quickly jumped on it, because this meant that I could actually now work with him and look at problem statements in strong collaboration with him. And the things that I started to look at is, to come back to this particular question first, is okay, so this was when I finished my PhD and went the spintronics route, trying to create new transistors and understand what is happening to this sort of transistors. What ended up happening was that there was no slowdown. Like, engineers working in CMOS were much more smarter, and they were able to tackle all these challenges that this community was facing, and kept on marching and creating these sort of Moore's law. But what did emerge out is there was new trends in computing that started forming. Like it is still important to create more and more fast transistors to solve very concrete specified tasks, which humans are very challenged to do. But there was this trend of looking at there are many tasks which humans are very much good at doing. There's this sort of domain-specific tasks which were becoming much more important, these data-driven tasks with the emergence of so-called artificial intelligence. But these transistors don't do that very well. So if you can also create devices which can accelerate these type of tasks, which are more AI driven, those domain specific. It's not a general purpose computer which we'll use for every task, but for just specific tasks which are very, very important. If one can build such devices, that was also being very important. And the other trend that was happening at the same time was that CMOS is not going to go away. It's very hard to beat it. But what was important is that you could add new physics on top of this CMOS, which is represented by this X, and potentially try to tackle the problems in this domain by combining CMOS with new physics. And this was sort of epitomized here at Purdue. At that time, Professor Datta's group, both persons Jan and Kerem here, were looking at this sort of new forms of computation, so-called probabilistic computing, where the bits of here, the basic building blocks of such computers, are not the ones which are like CMOS, which is deterministic to +1 or -1, but they kept fluctuating between zeros and +1s and -1. And it turned out that the main power of such a machine is if you have n basic building blocks here, you could represent 2 power n amount of information, encode 2 power n amount of information in this, and that allowed to really solve big problems, could potentially allow to solve very big problems. And the phenomena that they were using to create these sort of probabilistic bits was again the magnetic tunnel junction that I spoke about, which I learned during my internships, where they were using these magnetic tunnel junctions and the rate at which they can flip up and down, using that to create these sort of cool devices. But one issue with them was the fact that the electronics could be very, very fast, but these magnetics of these particular systems was a bit slow. They could not match the speed of the electronics. And this was one of the first problem statements that I worked with the team over there and solved, provided the idea of how you could actually speed up the magnetic fluctuations also and create technologies which could switch at much faster rates, which was later on demonstrated by both the Tohoku and IBM groups. So that was one problem statement. The last problem statement I want to talk about today is then the nice thing about Purdue is it's highly collaborative, and that gave me an opportunity to also continue along the lines of this quantum aspect that I learned about using the spins as sensors, and with a range of many distinguished faculties who are sitting here also, Professor Jihong Shen, Jorg, Sasha Vlad, and Yong. I was given this opportunity to also use these quantum bits to create new kinds of sensors. What can we push the technology that we demonstrated back in my postdoc area? And here, working along with them, we sort of expanded these dimensions into different directions where we could enhance the sensitivity to electric field sensing, not just magnetic field sensing, and other phenomena that were later on also demonstrated by other groups here. So, and along the same lines, there was this opportunity to now use all these learnings to develop new courses, which Purdue again is very much supportive of. And we ended up developing a micro-master's program in quantum technology and sensing. And this was about the time when I added one more human interaction to my family, who's also there, joining here, supporting me. And I would again like to thank my wife for during this time. This was the time of COVID. And this was a time when I always committed to give this video lecture, and she was a new mom, so I could not support her well during that time. But she single-handedly again stood up and said that she was going to take care of her and grow her into a nice, inquisitive, kind child. And just to tell her about this inquisitiveness, she asked me this question like 2 days back, where she said that, what have you discovered that helps society purposes today? Because she came to know that I am a researcher. And with that, I would just like to give my final vision. Hopefully, I can answer that question someday for her. And the final vision that I would like to essentially take moving forward is to continue along, just adding more interactions, both for the physical system that I work with and for the family and for my collaborators and mentors, or all students, new students who are sitting here, and create these sort of new devices which could allow us to do computation and sensing in this new learning world. So with that, I would like to just stop and thank you for your time.
So one of the things that I forgot to mention when I was introducing Pramey is that he's also won teaching awards, and I think that this talk is I think good evidence of why that happened. I hope everybody got to learn something very cool from this kind of broad sweep of history. We have a few minutes for questions. Two minutes for questions. Jihan.
So, Pramey, I really enjoyed you describing your entire from a curious child until now. I really established researcher, and then like during your probably master degree or bachelor degree time, you were discouraged to become an experimentalist. But now I noticed that you are also encouraging your students to become experimentalists. So how did you switch again back to that path?
Well, I would say that I was encouraged to work on experiments, to do things that are relevant for experiments, but I was just personally not good at doing those hands-on experiments. But the students that I've had, particularly one sitting here, Abhishek, has led our experimental efforts where he's very good hands-on doing those things. So I'm just using him to try to see if some of the ideas could work or not. Yeah.
So you want to bridge both.
Yeah. So I still want to maintain this working at the interface or experimental theory. That's it.
Ask. I'll ask a short question. So I think an interesting thing that you mentioned was how you were inspired to get into some of these fields by reading books by Supriyo back when you were in undergrad, and now you get a chance to work with him. This is maybe a meta question. Can you maybe talk about, I think you've demonstrated this in your own work too, can you talk about the value of not just doing our work for ourselves, but being able to kind of express these ideas in ways that other people can see them and latch onto them and get ideas from them? Because it feels like that's had a big influence on you.
Yeah, I certainly feel that is very, very important. In fact, I have some words from Supriyo and sort of Feynman's. I think there's this so-called Feynman technique that you may learn about, right? That if you can explain what you do to, let's say, an undergrad or 5-year-old, can you bring this down to that level? Unless you can do that, you would have not really understood things. So it goes both ways. If you can do it that way, I think it will allow you to understand things much better. So I'm fully subscribed to that.
Let's thank Pramey again.